Today, we're going to be looking at magnetic fields and angles. If you remember from last lesson, we finished off with this particular example right over here and briefly took a look at a couple examples here where when the current and the field were in the exact same direction, there was going to be no force. And in that situation, you had a value of 0. And even in this case where you had a current going one way and the field going the complete opposite direction, you're also going to have a force of 0. So when we begin working with angles, we need to really break it into the components, into the x and y components. So for a force to be exerted on the wire, the magnetic field the wire is in and the current flowing through the wire must be perpendicular, aka making that 90-degree angle. If the magnetic field and the current aren't perpendicular, we need to break it into the components to determine, well, what portion of the magnetic field is actually perpendicular to the current. So in this example right over here, what you see is a field going, let's call it north, with a current going 25 degrees north of east. And so I broke it into the different components, into the y current component and then the x current component. And so if we're looking at only that which is perpendicular, we want to determine, well, what is this value for our the x current portion right over there? And so if we were to have used the 25 degrees, I know it gets a little bit confusing because there's cos and the formula that's given is right over here. Our force is equal to our electric or our magnetic field, times our current times our actual length multiplied by sine theta. If we're going to be using this value right over here, just remember the concept here. What's going on here? What do we actually want to find? We want to find the piece that is actually perpendicular to the field. And so in order to do that, if you were using this 25 degrees, that's why I ended up saying cos 25, because you would have wanted this adjacent piece of this triangle. If this was a triangle right here, then the adjacent over hypotenuse would be cos 25. If you take the 65 degrees, which is just 90, take away the 25, in this case, opposite on this triangle is now the x portion, the x component of the current. And so now you could do opposite over hypotenuse, and then you could have the sine 65. So just be aware of that. So because you want to have the component of current that is perpendicular to the field. So when you're going through these calculations, just think it through. Just don't blindly plug in a value. If you're given 25, oh, it must be 25 over here. Don't do that. Make sure that you're actually drawing it out and trying to make sense of what you're actually given. All right, let's jump into the examples. A 10 amp current flowing north through a 2-meter long wire is in a magnetic field with a strength of 6 Teslas at a 30 degrees north of west. So we have our current going north right over here, and we have a field that is going 30 degrees north of west. So here we have our field, 30 degrees north of west. And what we want to do is break it into the different components right over here. So we're going to have the field over here. This is the x value. And then we also have over here the field that is the y value. What is the magnitude and the direction of the force exerted on the wire? So the first thing that we can do is look at the right-hand rule. So remember, and again, I'm not going to give this away just right away, so I want you to attempt this out. Where is the current pointing? It's pointing north, and so what are we going to use? Are we going to use our palm, our fingertips, or our thumb? All right. What about for the field? Are we going to use our palm, our thumb, or fingertips? All right, well, now give that a try using the proper positioning for your thumb and your fingers, and then determining where is your palm facing. And if you're curious as to, well, which value are you going to use for your field, it's going to be that which is perpendicular to your current. So if your current is going directly north, then it's the portion of the field that's going directly west. So take a look. What's going to happen here? If you had your force should be pointing out of the page. So at least we've now determined what's the direction. Now we can do the second part there. Well, what is the magnitude? And this part is the easier of the two pieces, I believe, because you're just going to be using your formula here. So it's the magnetic field multiplied by your current times by the length times by sine theta. And so I'm just going to punch that in right over here. And we get 6, we have 10, we have 2 meters, and sine 60. And so this would be another one of those examples. Look at this, sine 60. Over here, the way I drew it was 30 degrees, this being 30. If we did do opposite over hypotenuse, our opposite is going to be our y value. And so in this particular case, we can't actually use this 30 degrees. And so it's very, very important to understand that you're either going to be using sine 60, or you're going to have to just modify this formula a little bit and go with cos 30 degrees there. So it's one or the other. The biggest piece you need to remember is that it has to be perpendicular. Current and the field has to be perpendicular. That's going to help you to determine what the magnitude of the force is. So that's where the 60 comes from. If you multiply it out, you get 104 newtons. There's 3 sig figs for all of these, and so I have 3 sig figs in our final answer. And yes, it is coming out of the page here. For the final example, we have a 3-meter long wire in a magnetic field with a strength of 4.56 Teslas east. So this time we have our magnetic field to the east. If the current flowing through the wire is 2.15 amps, 25 degrees north of east. So here's our current. We have 25 degrees over here, north of east. And again, we can break this into the different components right over here. So we're going to have our current in the x direction. We're going to have current in the y direction. In this particular situation, we're going to be wanting this value because our current in the y direction is going to be perpendicular to our magnetic field over here. And if we're taking a look at our angle, the 25 degrees opposite over hypotenuse, we will be using sine theta. So in this particular case, we will be using that 25 degrees. At this point here, we're going to be doing the same two things. We're going to be determining what's the magnitude, what's the direction. So I like to start with, well, what is our direction? So the same thing as last time, take a look and determine, okay, using current for the y direction here, which one are you going to use again? Is it the thumb, the fingertips, or the palm for your current? Do that now. And also place the proper part of your hand with the magnetic field here. And your magnetic force will be into the page. Now, for your formula, same thing. Plug it in here. You got your field, you got your current, you got your length, and sine theta. Plug all these values in here. So we have 4.56, so on, so on. Here's the neater version here. So magnetic field 4.56, your current at 2.15 amps, your length is 3 meters, and then sine 25, because again, in this case, opposite of hypotenuse, this is perpendicular, your current is perpendicular to your field. And you're going to get a final value for your force of 12.4 newtons, and again, that's going into the page. And this concludes the different sections. So the key thing here just to remember is make sure that you don't just blindly use the angle that you're given here for sine theta. So on this last one here, it was sine 60. We were given 30 degrees, but you needed to use sine 60. So just make sure that your perspective of what's going on here is always at the forefront of your mind. Make sure you're always looking to say what is perpendicular to the particular forces here. So we're looking at field and current, what's perpendicular to the two of them. Hopefully that helps, and good luck on your assignment.